Welcome back, guys. Today we'll be discussing about a new type of galvanometer in this video, which is a very interesting galvanometer. It is known as the ballistic galvanometer. So let's ballistic galvanometer. So this galvanometer has a lot of applications, mainly for measuring the amount of charge. So one of the application that we have here is to measure the amount of charge flown during an impulse current and one of the other applications is that it can be also used for doing the magnetic measurements, like we can plot the BH curve, which is the magnetic flux density versus the magnetic field intensity of a material. So that is one of the other applications of this ballistic galvanometer. So let's look at in detail how it is, how this instrument works. So the construction is very much similar to our PMMC instrument, very much similar to the permanent magnet moving coil instrument. The only difference is that there is no damping, there is almost equal damping. The damping coefficient is almost equal to 0 for this instrument. That is the major change in this ballistic galvanometer. So here let's see how we can measure the impulse current, or you can say the charge that is flown through a circuit, the charge that is flown through during an impulse current. So I hope you know what is an impulse. So impulse signal can be represented in this format. So this time interval is a very small interval, t1 to t2 is very small, and the intensity is almost equal to infinity. So that is what we call as an impulse, right? So but if you multiply these two, what happens is that this, let's say this is I versus t graph. So if you integrate and try to find the area under this curve, so integral t1 to t2 I of t dt would be a finite number, because even though it is not very much infinite value to which the intensity goes up, but then the time period over here is very short, that once you multiply these two you get a very finite number. And there is a signal that is known as the unit impulse. So unit impulse signal generally has an area of 1, area equal to 1. So this is an impulse signal, impulse current, which is there, which comes for a very short duration of time and just disappears just like that. So we'll see how we can measure this measure the charge flown during this impulse current. So this is of very importance, because there are lots of impulse that can be seen in our daily applications. So it would be very much good if you can actually find what is the amount of charge that flows in that very small instant of time. a very small instant of time. An impulse can also be compared to a lightning, because it happens in a very short duration of time. And yeah, so let's see how this can be done. So the torque, so in the galvanometer, let's say you have the coil over here and the permanent magnets in the coil, let's say. So here a small very the current flows for a very short duration of time. So this is the impulse current, let's say, that flows through this instrument. And what happens is that this will produce a torque, because of which the coil will start moving, turning into one of the directions. So a torque will be produced, and the torque will be equivalent to G into I of t, where G is B into A into N, the constant G, which is BAN, into I of t, which will be equal to the you can say the moment of inertia, which is J into d square theta by dt square, the moment of inertia in transferred due to the torque, J into d square theta by dt square. So this is the general equation that we can write over here. And since there is no damping, what happens is that this coil keeps oscillating, and we'll see how these oscillations can be measured. So here we can take this J inside over here, and we can rewrite this expression in such a way that d by dt of J into d theta by dt, so here J into d theta by dt can be written as omega, which is the angular velocity or angular frequency, and J into omega will become the angular momentum. So basically G into I of t is the derivative of angular momentum j omega, which can be written as the rate of change of angular momentum. The rate of change of angular momentum in this case. So from here what we can do is that we can multiply the small duration of time over here for which the current flows. So you get G into I of t into delta t, which is the duration of time for which the current flows in through the coil. So which becomes or you can write it as a dt, delta t dt, everything is the same thing. So it becomes d by dt of j omega into dt, which makes it dj omega, which is the change in angular momentum. This is no more the rate of change of angular momentum, but it is the change in angular momentum, right? So yeah, change in angular momentum can also be written as g omega, and where omega is the angular velocity immediately after the impulse current flows. So here G into I of t into dt, so this quantity is our charge. So G into Q can be written as j omega, because that is the complete charge that flows, and omega is the angular velocity immediately after the impulse current flows. So ng is the moment of inertia. So from here what we can write is that q, the charge, is can be expressed as j omega by g, or omega can be written as omega is equal to qg by j. Now so here what we do is that what we'll write what is the kinetic energy. The kinetic energy immediately after the impulse current, that is the kinetic energy picked up by the coil by the rotating coil, right? So kinetic energy immediately after the impulse current can be written as half j into omega square. So this is the kinetic energy that is picked up by the coil which is at rest. And let's say the coil is, let's say this is the coil, and it keeps oscillating to and fro, and at the final point this entire kinetic energy is actually converted into potential energy because of the controlling torque provided by the spring. So the potential energy is found in the spring. Let's say the entire kinetic, here what happens is that the entire kinetic energy is converted into the potential energy. So the final potential energy at the final point can be written as the final potential energy in this case can be written as half k is a constant, into theta f square, the spring constant, into theta f square. Theta f is the final angle theta, so this is the final angle theta f square, which can be equated with the initial kinetic energy, because the entire kinetic energy just gets converted into the potential energy at the final point, which is over here, and then it converts back into kinetic energy, and to and fro it continues. That is how the oscillation happens. So here if we equate these two equations, you can cancel out these half and half, and then from here for omega we can substitute this expression, that is j into omega is qg by j the whole square. So from here what we get is this is equal to j into q square into g square by j square. So j and j can be cancelled, so k theta final square can be written as in this form. From here we can find what is q, so q square is equal to we can take the j and the g square to the other side, so k j into theta f into by g square, right? Yeah, by g square is equal to q square, or you can write q is equal to root of kj whole divided by g into theta f. So this can be taken as a constant, and Q will depend upon the charge. Q will be proportional to the final angle theta in the ballistic galvanometer. So this is how, and theta f is the value that we'll measure from the pointer, the moment of the pointer. What is the theta? What is the angle theta that is being achieved during the impulse current? Because this keeps oscillating for a certain period of time, you can easily find what is the theta f. From there you can find what is the charge that is flown through this ballistic galvanometer. So this is the way how we can find what is the charge that is flown through the ballistic galvanometer. Now we'll also look at how we can do the magnetic measurements, which is the BH curve. How we can find the BH curve for a magnetic material, right? So here what we do is that we take a magnetic material, let's say in this we take a magnetic material or a magnetic core in this shape, and what we do is that we'll connect let's say a meter, then we'll connect a switch, and we'll connect a source, a DC source, to this magnetic material, and let's say we put some windings over here in order to magnetize the core. And it's similar to a transformer. From the secondary side we take another coil, and we connect the galvanometer over here, right? So what we do is that initially the switch will be closed, and what we do is that we'll suddenly open the switch. So there would be a quick change in the flux in the magnetic core, and because of which there would be a impulse current that would flow through this galvanometer. So let's look at what are the governing equations over here. So what happens is that when the switch is opened, I becomes 0, and flux phi also becomes 0, which means that there is a change in flux, because initially there is some flux because of the current that is flowing through this circuit. Let's say this is the current, because the switch is closed in the initial state, and there is some kind of some amount of flux phi that is actually flowing, and it suddenly decreases to 0 because which there is a change in flux linkage in the secondary coil. So here there is a change in the flux linkage in the secondary coil, and because of which you will have an impulse current that would flow through it. So let's say the change in flux linkage, in this case change in flux linkage of secondary coil can be written as phi n2 minus 0. Let's take this is n2 and this is n1 number of turns, so phi n2 minus 0, which is same as phi n2, right? And this can be written as d psi, which is the change in flux linkage. This phi can be written as b into a, which is phi is the flux and b is flux density into area, so you can write it as b a into n2 d psi in this case. So from here what we are going to do is that we are going to look at what is the rate of change of flux linkage. So in this case, the rate of change of flux linkage can be written as d psi by dt, d psi by dt, which is equal to BAN2 by delta t. So rate of change of flux linkage is also can be also written as the EMF that is produced in the secondary. So EMF that is induced, EMF induced in the secondary coil. So let's say R is the resistance of the secondary coil. So now I can be written as the EMF divided by R, and there is definitely an inductance, but it doesn't make any difference even if you consider the inductance in this case. It is going to balance out, because of which we won't be looking at the inductance. I mean, we can look at the inductance, there's no issues, but it doesn't make any difference if at the end of the derivation. So we'll just go with the simple derivation with the resistance over here. So here we'll get it as BAN2 by delta T into R. So this is the current that would be flowing through the secondary coil, and let's say we can multiply, let's find what is the charge that flows through the secondary coil. So the total charge flown in delta T time can be written as I into delta T, which is equal to BAN2 by delta T into R into delta T. Delta T and delta T can get cancelled. Now I into delta T can be written as Q, right? So from here we can write what is B. B is Q divided by Q into R divided by AN2. So this is the final expression for finding the magnetic flux density using a ballistic galvanometer. So Q we have seen how we can measure Q in the last part of this video, and from there R and A and N2 remains constant, so we can easily find what is the value of B. Now the magnetic field intensity, H is given by I into N1 by L, and the MMF by the length of the core, mean length of the core. L is the mean length of the core. So here I hope you know what is the length of the core. The core is in the form of a circle, so you can take the circumference, which will be the mean length of the core. So from here the magnetic field intensity can be varied using changing the value of current. So let's say in the circuit you can use a rheostat. Let's say you have a rheostat over here, and then you can connect an ammeter, and then you can connect the switch. So from here you can connect the primary, right. So by varying the rheostat, you can vary the current in this coil, and by varying the current you can vary the magnetic field intensity, and you can find what is the corresponding magnetic flux density corresponding to each values of field intensity, and you can plot the BH curve for any magnetic material. So I hope this video is clear. If you have any doubts, we can clear it during the live session. Right, thank you guys, have a nice day.